Hola.
Hola, hola, profesor.
Cuando estamos esperando, hay preguntas.
Yo no.
Muy bien.
Hello.
All right.
Hi. Good afternoon.
Very occupied day.
Yeah, just a comment. Here in Chakaltaya mountain, here around La Paz city, we have a Cherenkov detector. We use water, big tanks, and we study secondary particles produced in the atmosphere. We think that the primary photon comes from gamma ray burst. And it's
What range of energies are you sensitive to?
Sure, 10 to 10 electron volts. But 10 to 10 to 10. I'm not sure. Because
mega electron volts?
Yes, yes.
Okay.
Because it's gamma ray burst. Yeah. Just a comment.
No, I mean, it should be relevant to what you have done in the past. Yeah. Okay, good. I think we're almost at a quorum, 8. So today we're going to talk about atomic physics and actually delve into quantum mechanics a little bit. How many of you are familiar with that? None of you have seen that before? No?
Atomic physics.
En pregrado tomé un curso de física atómica, pero...
Sí, no, con funciones de wave functions and spherical harmonics and right, quantized levels, that sort of thing, right? So I mean, hopefully you've seen it before. Otherwise, you're going to be in for a shock. Macarena, you look very worried. You never took a quantum mechanics course, or you took it and you didn't like it? Okay.
I didn't like it. I don't know.
Yeah.
I think that it's like a love-hate relationship. I would state it like that.
Yeah. I think the mathematics of it are hate, and the weirdness of it is also a little bit of hate.
But it's awesome. But you can explain that. But then you have the mathematics and everything is chaos.
Yeah.
So.
Yeah. Okay. Well, I'm going to largely skip over the mathematics, but yeah, I just wanted to gauge sort of the level with which people are comfortable with it, because this is a very broad strokes thing, assuming you've spent a semester doing it, right? So this class in particular is more of a review of that, and I mean, ultimately, we don't need a lot of it to talk about what we actually observe, right? I mean, the underlying, why you have a certain physical term there, or why there's a certain number there that, is multiplying this, that's fundamentally built on quantum mechanics. But in terms of the everyday sort of aspects, it's sort of a lighter touch, right? And so you don't need to work with spherical harmonics and things like that on on a daily basis to sort out, line ratios or understand exactly what's going on. Okay, so with that introduction, let's get to it. And here we go. All right. Okay, so, right, I mean, mostly we've been dealing with continuum processes so far, right? And we haven't really talked about the microscopic or atomic scale processes. And so once we kind of delve into those, we have to be a little bit more careful about how we treat radiative transfer. And so, obviously macroscopic theory is fine on large scales when you can average over things, but on a specific atomic scale, we need to actually deal with quantum mechanics a little bit just to understand the absorption and emission coefficients and how we treat them when we're talking about, a complex system like an atom. So the quantum calculations here were typically we can understand things in terms of sort of calculating a de Broglie wavelength for a particle, and this should be larger than the dimension L that determines the conditions of the problem. And this kind of gives us some sense of when we can be macroscopic or microscopic. And so, an example here is the electron orbiting the nucleus. And so applying classical theory to that system fails, right? The electron is attracted to the proton and spirals in, and it continually is losing energy in this process. But we know that an atom is a stable system. And so there's something else that's going on that dictates the physics on that scale. And typically we can understand this based on whether things are smaller or larger than this de Broglie wavelength. So, there are many places where atomic processes are fundamentally important for properly explaining astrophysics, right? And there, for instance, are emission lines that are strong cooling outlets. So in the infrared, you have dust, and gas that's heated to not very high temperatures, 100 Kelvin, and the dust will radiate some of that energy away, or most of the energy away, but certain emission lines from carbon, nitrogen, oxygen, those will actually radiate 10 to 20% of the total energy away, just in those 3 emission lines. And so, right, you have, if you really want to physically understand the system, you need to sort of incorporate both the sort of complex systems and complex emission that comes from dust, and then also from lines and from other processes. Okay, so we're just going to review this class. We're just going to review the basics, so we're all kind of on the same wavelength, as it were, for sort of describing these systems. So, we can go back to your early undergraduate days of talking about classical quantum mechanics, and we have the Bohr-Sommerfeld theory. And this, one of the key things here is that the action is quantized, and that this quantization, you have a quantum number which is related to the electron motion. And so you have some probability of the electron being somewhere, but it's also quantized. So the probability is, it will be sort of here, but then with some uncertainty. Right? And this leads to quantum states and quantum levels. And within those, there's a probability that the electron will be sort of within a certain space that it occupies. The other one, that's sort of coupled with this is the hydrogen uncertainty principle, which states that we don't, with any certainty, understand both the position and the momentum of that state. Right? We can only understand where it is to some level which is less than the Planck constant. And then finally, there's the exclusion principle, which suggests that we can sort of occupy quantum states as long as the properties of that particle are distinct. And so, for instance, electrons have a spin, and so if they have opposite spins, they can occupy the same space. But if they have the same spins, they can't. Right? That sort of thing. And so the spin direction allows some more flexibility. And so then within the sort of Bohr summerfield theory, we have the electrons are in motion around the nuclei. The nuclei have a charge Ze, the electrons have a charge E, and sort of the first, the 0th order state is you have circular orbits in a Coulomb field, and we can plug that in and derive a radius, or a classical electron radius. However, when we force quantization here, then we have to sort of integrate this momentum over some phase space, and we then integrate the momentum is this, and so this thing here has to be quantized, and so this leads to levels or sort of radii, which are the Bohr radii, and so the velocity goes as sort of this quantized levels, and the Bohr radii, depending on whether it's in level 1, level 2, level 3, will look like this, right? And so those are kind of quantized for the hydrogen atom. And then you have this extra factor Z that goes in for larger atoms. And this also is just taking into account, not sort of extra levels of complexity here. Okay, so hopefully this is all fairly well ingrained in your memory already from early quantum mechanics. And so to refine these approximations, you have the finite mass of the nucleus, and we can think about it in terms of a reduced mass. So you have the reduced mass is related to the electron and the total mass of the nucleus, and so electrons that are further out in further shells will see this sort of reduced mass. And this also leads to a variance as a function of isotopes and elements. So the radii will slightly change depending on if there's an extra neutron in the nucleus or not, right? The other sort of complication is that you can have elliptical orbits. And so this then means instead of having a purely radial form, functional form, you have radial and azimuthal components. And so you have a radial component, which is dictated by this sort of n level, but then you also have an azimuthal component that you have to integrate over to find exactly with what probability an electron should be in three-dimensional phase space. And this component is typically given by this azimuthal quantum number, which is often denoted as the orbital angular momentum. And so that's typically denoted as L. And you typically see this in sort of L plus 1, where L can be 0, 1, up to n minus 1, where n is this here now. So that is, gives a better approximation of the properties of atoms. And then we can talk about further refinements where we're treating things in a more probabilistic, relativistic way. And so if we have n and we have L, which are the principal sort of quantum numbers, we can define a semi-major axis and a semi-minor axis of an orbit, right? So we have the elliptical orbits. And so the major axis is given by this, and the minor axis is given by this. And so we can then build out what the structures look like as a function of the n levels and the L levels. And so we have the ground state might look like this, then we have the first excited state, and we have different probabilities in these various axes. And then the second n equals 2 state, and we have then 5 possible orbital angular momentum states, and then n equals 3, and so forth, right? And they get more complex in terms of the phase space that they can kind of occupy. Everyone remembers this, correct? No one's scratching their head still, or yet. Okay, no complaints. So the other thing, another way we can kind of think of this is as a function of energy. And so each state is a further radius away, and so generally has a lower amount of binding energy. Right, so if you give that state some energy, you can pop the electrons off and they become unbound. And so the ground state is the most secure, and you need 13.6 eV for the height for a hydrogen atom at least to take this electron and move it to infinity. Whereas the n equals 2, 3, or 4 states, you need less energy to do that. And we can calculate the energy based on just the semi-major axis, and orbits of the same n but different L typically will have the same energy. And so the energy is just given by this equation here. So related to the radial Coulomb binding and its velocity, right? And so if we insert our quantized radii in here, then we end up with quantized energy states, which look like this. And so for hydrogen, this is 1, and so then we have our sort of lowest energy here. And so if this is 1, this is sort of the highest amount of energy. If this is 2, this is now 4 times less energy. If this is 3, it's 9 times less energy, and so etc. And then of course we have the what is it here? The reduced mass, right? Okay. And so if we were to calculate up these quantities, they give us this minus 13 eV for z equals 1. So we can then think of transitions between these different energy states, which might happen. And so if you have a transition from one of the higher states down to the ground state, this is known as the Lyman series. And so the 2 to 1 transition is Lyman alpha, the 3 to 1 is Lyman beta, the 4 to 1 is Lyman gamma, etc. Right? And you have all the way up to n equals infinity if you want, but the energy levels go up very, very, or they asymptotically get to this point where things are unbound. Likewise, you can have a transition from these higher states to the n equal 2, and that's the Balmer series, so H alpha, H beta, H gamma. Then to n equals 3 is the Paschen series, to n equals 4 is the bracket series, and so forth. And so these, typically will have this transition is a change between this energy and this energy, right? And so this will have a sizable fraction of the total amount of energy. So this might be a 10 eV photon. And so that energy will come out in the ultraviolet. This has less energy, so this comes out actually in the optical, as it turns out. This comes out in the near infrared. The bracket gamma series also comes, so the bracket series comes out in the infrared as well. And so the change in energy states here, we can relate to a photon that is emitted in the process of going from a higher state to a lower state. And that photon is just the difference of these two energy states, which can be sort of summarized by this difference of 1 over n squared minus 1 over n squared, right? From the higher state to the lower state. And then this factor. Okay, so this can typically be, all of these constants can be denoted as the Rydberg, and the Rydberg has a value of 13.6 eV, right? Okay, so we then, if we want to go to a stricter level of approximation, if we want an exact solution of where the hell the electron is, what's the probability of it being in any sort of one place at a time, then we have to open up our quantum mechanics books and break out Schrodinger's equation. right? We need an exact equation here that can predict where the electron will be in its various states. And so this we need a particle wave function, which is denoted by this here, and we need to solve this using the time-dependent Schrodinger equation, right? So we have the time derivative of our wave function is equal to our Hamiltonian times our wave function, and so if we neglect spin, relativistic and nuclear effects, and all of those sort of complications, the Hamiltonian can be broken down into this thing, which is ugly, but it's simply summing up all of the possible states that this thing can be in. And, it's sort of as simple as that. And we have states where we have an I state and a J state, and we have some transitions between them. There's some probability that there can be a transition. And so, typically we often only deal with sort of stationary solutions of this problem. And so you can write the wave function as sort of two parts here. And so you have a radial dependent form and a time dependent form, which you can separate out. And this simplifies things a bit. Although there is potentially some crosstalking here at a minor level. And so then we can solve this time-dependent Schrodinger equation by just sort of, applying this thing here. And so this derivative here then just becomes E, right? And so we have a pretty sort of easy way of handling this. Well, typically, an atom's going to have, unless we're talking about a hydrogen atom, it will have more than one electron. And so this makes the Schrodinger equation much more complicated to solve. And so for larger atoms, we make a practical assumption here that we have the electron moves in a field of the nucleus plus the average potential of n-1 electrons. So typically, we think about the innermost electrons will mostly be influenced by what's interior to it and not so much about what's exterior to it. And so you can kind of deal with that. And this is called the self-consistent field approximation. And ideally, if you assume an average potential, which is spherically symmetric, then this simplifies things quite a bit. This is known as a central field approximation. And so that then means that for large radii, the nucleus ends up being shielded by some interior electrons. And for small radii, the nucleus dominates and the outer electrons have this spherically symmetric influence, which doesn't have a strong effect on the interior electrons. That isn't, there are some minor modifications to that. And there are some exceptions to that, but in general, it allows you to do pretty well in terms of predicting. Right? And so we then can think about this potential as taking a dual form where you have a sort of z divided by r component and that goes, for r as they go to 0, and then at large radii, you have a z minus n plus 1 divided by r, which goes out to large radii. And so if you kind of match these two things, you get a decent approximation of what's going on. So then thinking about this Schrodinger equation now, and the Hamiltonian was initially a sort of radial one. We can divide the Hamiltonian into a couple of, or rather we can divide the wave function here into radial and azimuthal components. And so that's what's done here. So we have a radial component and an azimuthal component. And so the radial component is nice. The azimuthal component is where things get complicated because we have to start dealing with spherical harmonics. And so we have now factoring in our initial n level our orbital angular momentum level, and we also have a spin angular momentum quantum number here as well. And so we then can talk about spherical harmonics, and this is the lovely equation for spherical harmonics, which is related to the different quantum states that they're kind of factored in here in L minus absolute values of M and 2L plus 1, etc. And then you have an extra factor here, which is giving you the sort of sense of this if it's spin up, spin down. And then you have the actual probability of it existing in some portion of azimuthal space, right? And that's what kind of leads to this, these probability sort of slices. Okay. And this thing here is this associated Legendre function. And so this spherical harmonic then is associated with the orbital angular momentum, which we can think about, the orbital angular momentum is just R cross with the momentum here, and it should obey the following relations. So this L squared times the spherical harmonic is equal to, so this is the total angular momentum here from this sort of idea. This should be equal to the orbital angular momentum numbers, so L times L plus 1. And then we also have the Z component, which of this orbital angular momentum, which should be equal to the M component. And M here takes on these values. Right, so this ML typically is abbreviated as M, and so you also can often see the L numbers here, which go from 0, 1, 2, 3, etc. These are often denoted by letters. And so for a typical, say N level 1, we have the possibility of just having N minus 1 L levels. And so we just have the 0, so we just have the S state. And then for N equals 2, we have L can be equal to 0, 1, or minus 1. And so those are the S or P states, and so forth. And then typically this spherical harmonic is thought to be what's called orthonormal, which means that if you have a if you integrate this times this other function or sort of other set of spherical harmonics, integrating over all of the solid angle, you should end up with sort of these delta functions in this space. Okay, so that's a lot to handle. The wave function here, the radial portion of this is typically solved by a solution where you have the energy levels, you have the double derivative of this wave function with respect to the radius will be equal to this quantity, or rather this combination will be equal to 0. And so here again, this is the, yep, any question? I'm hearing somebody. No, that was Roy, okay. So, right, so this VR, going back here, where was our V definition? I missed it. Yeah, where did I define VR? I can't find it. I thought it was defined somewhere. Did I not define it? No, I guess I didn't define it. I'm blanking on what it's supposed to be. Ah, here, there we go. It's just the sort of Coulomb potential case, right? So this is the radial dependence, which is given by this. So this thing here is sort of the radial dependence of this wave function, or offsetting that. And so we have that, again, this thing will be normalized such that it will also have a delta function. So if you were to integrate it over all radii, it's going to collapse down at a certain n level. And so likewise, this, if you integrate this over all of this odd angle, it's going to collapse down at a certain L or n level. Okay, so this, the square of this wave function here then provides a probability of the electron being anywhere between R and dr for the pure Coulomb case. So this should basically satisfy this. And so if we redefine the radius in terms of a quantum number and z, then this wave function for these individual quantized radii will look like this. And so then again, this is now an associated Laguerre polynomial, which is another lovely function. But this has an exponential form and then some sort of number related to the quantum state. And so we then have the energy levels associated here are going like this. Okay, so this glosses over an entire semester of quantum mechanics. Most of it because we're not going to deal very strongly with any of this. So I just wanted to kind of remind you it was there more than anything else. Are there any questions so far? No, okay. It's all sort of, is it all coming back to you at least a little bit? And Macarena is probably having bad nightmares, I guess. Okay, so if we actually plot out these wave functions in a radial form, right, we have a probability for, say, the 1s state where the electron is going to be somewhere in this range here, right? And so it'll have some probability which peaks right here, which is kind of where the fundamental radius that we calculated based on the Bohr-Sommerfeld approximation was, but then there's some probability that it's outside of that. And then likewise, you have the 2s state, you have the 3s state, the 4s state. Then you have the 2p states, and right, so they have some probability of existing within this radius regime here. And then if you look at this in a three-dimensional sense, then you have something which, well, this is a two-dimensional slice of 3 dimensions, just for the hydrogen wave function. But you have some probability here. So this is for, I guess, the 2 state. But you also have secondary sort of probability. So while this has a high probability in the 1s state of being here, it may also have some secondary sort of probabilities, where the 1s state not so much, but so the 4s state actually has some non-negligible probability that it exists here or here or here, right? So it can exist at smaller radii with some possible probability, and that's denoted by this particular wave function here. So you see that it has some probability of existing closer in too. Likewise, this is the 2p state, and so you can see that it has sort of a probability which looks like that. So these things, when plotted in 3 dimensions, come back and start looking like this now. Okay, so hopefully that aspect of everything is fairly clear. So once we start getting to higher level atoms, basically this is the same as many electron systems, right? So as we get to higher values of Z will have multiple shells and so forth. For a hydrogen atom, we basically just have the n levels, and we don't have to deal with much of the other things too much. So we have the principal quantum number, which is n. We have the orbital angle orbital angular momentum quantum number, which is L. Oh, sorry, actually I screwed up. And this M, there's two different M's here. So this one is the magnetic quantum number, which is given by this. So all of this, these spherical harmonics are the magnetic quantum number, not the spin. Sorry. And then you have the spin quantum number. Right? So you have n goes as you can think of it as 1, 2, 3, 4, 5, but you can also consider it as L. And so if you had L equals 0, 1, 2, 3, 4, 5, then n would be L plus 1, L plus 2, etc. Then m goes as L as well, between minus L and plus L. And then the spin state is plus or minus 1/2. And so the typically a major simplification is to take the wave function of each electron and multiply it. So I have a combination of products, which are 1 electron, 2 electron, etc., up to the end state. And so then the overall quantum, the overall wave function of the atom is this combination of products. And then we would, then sort of deal with them appropriately, or deal with the central field approximation and say, okay, these ones don't affect this at all, and so forth. And for the outer shells, they experience something which is slightly shielded. Okay, so here, this A value has a specific set of quantum numbers. The B value has a specific set of quantum numbers, and so forth. And then the products will form a complete set for the atom. And presumably these provide an adequate description. That isn't everything, because we still haven't really accounted fully for the quantum nature of the particles yet in this sort of scheme. So I mean, this does account for the probability of them sort of existing in certain regions. However, there are some extra rules we need to put into place that need to be satisfied here. And so one of those rules is, that electrons up to now have been identical, and we really can't determine exactly which electron is in what state. And so the way we would sort of settle this is to do a sum of linear combinations of all of the different states to really understand which electron is where, or probabilistically kind of deal with which electron is in which state. And so you have to sum over all of the permutations, and this will be sort of 1 over square root of n, n exclamation, which is the sum of all these different permutations, or all these different possibilities. So, however, when one has this combination, we need to satisfy the Pauli exclusion principle that we can only have electrons, so we can have electrons that can be in the same orbital state as long as they have different spins. But if they don't, if they have the same spin, then they have to be separated out, and they can't exist in the same spin, in the same states. And so we have this extra factor here, which is EP, which comes in here, and basically the EP is either plus or minus 1, depending on if P is an even permutation or an odd permutation of this set, and such that 2 electrons can maintain the same orbit, it'll subtract out. And so the wave function then ends up looking like a sort of determinant matrix here of the different individual components for each electron state. and you then have to sort of go through here and deal with which one, pick out which one of these actually ends up being the sort of right component for that. And so this calculation of determining the different states and determining changes between states, this gives you the full atomic structure. Right? This is effectively what's dictating what an atom looks like. Or I guess the other way to think about it is the atom looks like it looks like, and this is an approximation of that structure. So we can then think about this sort of structure, and we can think about it in terms of the energy levels, right? So if we go back to here and notice that the 4s state, for instance, has a probability of even existing down here at a relatively low radii. Right? If you take the average of this energy state, it will potentially be lower than, or higher than say the 4d state, which seems to be slightly lower in. And so if you think about this in terms of energy levels, or rather in this case, they're sort of higher up, but this 4s state ends up having an energy level which ends up being slightly lower than the 3d state, or the 5s is slightly lower than the 4d, but the 4p is lower than the 4s, etc. And so we have some notation of the structure, which is dictated by the shell number, which is given by n, which could be 0, 1, 2, 3, etc. We have also some value of the orbital angular momentum number, and so that can be 0, 1, 2, 3. And so this is typically denoted by S, P, D, F. This is typically denoted by K, L, and N. And so we can talk about the K shell, or the L shell, or the M shell. And so just to give you an example, you have something like iron, right, which has 26, atomic number 26, and so it should have 26 atoms, 26 electrons. And if you ionize it completely to the point where it just has one electron, so it's hydrogen-like, right? So you'll talk about the electron in the K shell when it's in its ground state. And so if you are to transition from one of the higher states to the K shell, right, you'll get a certain emission line, for instance. So if you think about these, if you calculate the energy associated with each of these orbital states, and then the sort of the energy level or the amount of energy you need to unbind that electron, or how much energy it's bound by, then you get a sort of sequence of filling the different states, right? And so you have shell and subshell filling, which goes in the order of energy. And so, typically you will fill this state first because it gives you the most energy, and so then you will fill these states, and so forth. When the atom is in its sort of least or most stationary state. And so generally these things are in order, except then you have the 4s state, which comes before the 3d state. The 5s state becomes before the 4d, and so forth. So the red ones are the things that are out of order for the most part, and so forth, which is a little bit better shown here. So that's fine. And so the higher S subshells basically become out of order. The S subshells are in effect closer to the nucleus. They're more tightly bound, if you will. And so the effective potential here, there's more binding energies to the electrons closer to the nucleus. Okay, so then the last sort of issue here to kind of fully make them quantum mechanical is to deal with the so-called orbital spin coupling. And so you have, this is known as LS coupling. Right? So orbital angular momentum is L, and the spin angular momentum is S here. And so the electron configurations that we've talked about here don't fully yet abide by the quantum mechanical sort of rules as they were. So we need to account for electrostatic interactions between the electrons and the spin orbit interaction. This is what's meant by the spin orbit coupling. And so in quantum mechanical perturbation theory, we have that this the total state of any ion will be determined by combining the spin and orbital angular momentum. And the sum of the total orbital angular momentum is the sum of the individual orbital angular momentum, and likewise the total spin angular momentum is the sum of the spin orbital angular momentum. And here our m value is changed to s here for whatever reason. And so we have a total orbital angular momentum, which is J, which is the L plus S values here, right? So it's the sum of the sums. And there are certain rules that follow what values of J are viable or not, and sort of how you can sort of build up the structure. And so these rules are kind of denoted as this LS coupling, which is also known as the Russell-Saunders coupling. And so a combination of S and L is also known as a term or a multiplet. And so the rules are as follows. They're known as the Hund's rules. And these are useful for estimating the energies of these different terms or multiplets. And so terms with larger S typically have lower energies. So if something has larger S, what it means is the spins are co-aligned. And so by the Pauli exclusion principle, you have larger separation between the electron states, right? If you have the same S value, then terms with larger L are in lower energy states. So large L means similar small L's, and the electrons are going around the nucleus in a similar sort of directional sense. Whereas if you have negative L, if you have different L's, then they're potentially going around differently. So what this again means is that they must be further separated again due to the Pauli principle. So if we have a multiplet or a term that's known, so we've defined S and L, then we can further split energy based on spin orbit interactions. And the splitting of the energies in this sense is known as the Thomas precession, and it's related to the total orbital angular momentum here. And so typically you have you have a shift that's going to be proportional to the total angular momentum state, so J times J plus 1. And so a change between these two values, between an orbital, a total angular momentum state J plus 1 and J, is going to be proportional to some constant here times this sort of combination here, which is the J plus 1 times J plus 2, and then the J times J plus 1. So it's the sort of upper level times its upper level minus the lower level times its upper level, right? And so if you multiply all these out, you just get that this should be satisfied by J plus 1 times some value here, which is 2 times C here, where C is this constant, which is greater than 0 if the shell is less than half full, and less than 0 if the shell is more than half full. And so it just is a preference that, okay, if the shell is relatively full, then there might be a preference to fill an empty shell at a higher level, right? And so that's what this is denoting. The full state here will then correspond to notation, which looks like this. So this capital L, remember, is the the end states. Actually, no, sorry, not the end state. This is the orbital angular momentum, but in a sort of capitalized fashion. So we have the values at F, P, D, F, but they're now capitalized. And then you have the J value, which sits down here, and you have 2 plus the S value, which sits up here. And so you can define different terms or multiplets by this. So this is the L equals 1 term, right? So P, and then the total J state here is 0 plus half for the spin, so it's 1/2. And then here we had the spin was 1/2, so 2 times, is that right? 2 times 1/2 plus 1 is 2, right? So that makes sense. And then here we have D, so D is 2. So actually, so this was L1. So if I get this right, yeah, so then to be 1/2 here, we would have to have, this would have to be, I think, -1, -1/2 to get 1/2. I think something like that. Likewise, here we have 2, and this would be, again, let's see, so we had, oops, this actually makes it easier, I think. Does it? Yeah, I always have problems with this. So let's see, the total angular momentum, let's say we have, yeah, actually this is, let's see, will this be 1 or 0? I think I'm slightly confused on that now. I think this should have a 0 too. Yeah. Yeah, so it should be that. I'm pretty sure this should be, oops, come back. 0, sorry about that. All right. Okay, so let's see, if this were P, it would be 1, and then we would have, yeah, if we had S is equal to -1/2, that would be fine. But then this, I have to remember how this goes. I feel like this shouldn't necessarily be absolute value. And so I'm trying to think of how that would work. Unless you could also have, well, this will have 3 different potential states. Yeah, I think I have to look at this table here to think about it better. So you have L could be any of these values. So you could have 0, 0, +1, +1, +1. And then you have the spin states. And so they could be minus or plus. And then you would be able to say, okay, and then you have the minus states as well. And so these are all of the potential possibilities, and a few of them are ruled out. So you have, if we have 2 electrons, for instance, in this spin orbit coupling. So the first one is in this state, the second one is in this state. If these 2 are in these states, then this is ruled out by the Pauli exclusion principle. If they're in different states, it's fine. And so likewise, right? So you have all, if they're in different L states, then you can have all the different permutations. If they're in the same state, you can't. And so that makes sense here. And then, yeah, this would be, okay, so we have the 2 possible S states. And so these are whether the source has a minus spin or a plus spin, and L equals 0. And so here we get rid of the J. We don't really show the J, but we have, if it's -1/2, 2 times -1/2 plus 1 should be -1, but it's only shown as 1 there. So I think it has to be the absolute value. Sorry for doing this in my head, but I always get trapped in this. So let's see. So if we had a +1/2, 2 times, oh wait, I see, okay. So this was 2 electrons, so we have one's -1/2, one's +1/2. And so you add them together and the total is 0. And so 2 times 0 plus 1 is 1. And then if they're both in the same state, you couldn't necessarily have that. But this would be 3s. I think that's the case. And then you could have an electron configuration where we had an s and a p, and that would look like this. And so forth. So these are sort of the individual electrons, and this would be the summary of the state of that particular shell, right? In terms of its total spin, angular momentum, and L number. Okay. And so the whole point of this is mainly that through the orbital angular momentum spin coupling, you have possible ways of splitting out different levels under certain conditions. And so you would have sort of an unperturbed state where the energy is the same, and through the sort of spin correlation energy, you would separate it out into a spin equals 0 and a spin equals 1 state for these 2 electrons. Then this individual one could be split out into these potential 3 states, depending on exactly what's going on when you take into account the residual electrostatic energy. And then when you look at the spin orbit energy, these states, in this case, this doesn't split out, but in this case, because these are in the same electron state, then these would sort of split out again, and you'd have slightly different energy levels there. So Rubicki and Lightman go into much more detail on this particular thing, but that's the idea. Mostly, this presentation is just to give you a nomenclature of when you see, some sort of thing talking about, okay, this particular state, understanding what that means, right? In terms of, okay, this P is denoting the L, the total orbital angular momentum. This is denoting J, and this is denoting S, the sum of all the spins, right, for these 2 electrons. Okay, so it's a way of compactly summarizing everything about this state. Finally, one could then think about the spin orbit coupling in something called parity. And so in addition to these total quantum numbers, there's another thing that people usually classify as the parity of a configuration. And this is the oddness or the evenness of the sum of the orbital angular momentums, extending over all the electrons in the configuration, but only over incomplete shells. So if the shell is complete, then it's outside of this sort of sum. But if it's an incomplete shell, then you would sum over, the n equals 2, the n equals 3, the n equals 4, etc. If they weren't completely filled. And this gives some idea of exactly how the shells are filled to some extent. And this ultimately what this tells you is something about the symmetry of the wave functions. And so we can also denote degenerate levels here by distinguishing the spin orbit coupling. And typically this is much smaller than the orbital angular momentum spin coupling. But this effectively splits the terms into a set of levels based on the total angular momentum. Right? So this is what this is doing here. And so the magnetic quantum number isn't counted there. But you can also, if you have an external magnetic field, this will break the rotational symmetry of the internal actions and break the energy levels. And we'll see an example of that in the next lecture. So taking all of that and sort of understanding the nomenclature, we then can back up a bit and talk about what we really need to talk about, which is, okay, we calculate these quantum states, right? And we calculate an energy level for each sort of electron where it is. And we want to know how we can do radiative transfer and how we can understand whether an atom is in an excited state and how it will spontaneously drop down to a lower state and emit a photon, how an an atom will interact with a photon field to either unbind the electron altogether or to excite it into a higher state, and then maybe eventually it will drop back down into a lower state again. And so we think about all of these things in terms of the transmission, or this transition between two levels gives an emission line, right? It gives a photon or it takes a photon away. And that photon has to be of a fairly specific energy, but there can be some uncertainty in the position of the electron, and therefore some uncertainty in the energy of that transition. But typically, the specific frequency of that photon will be related to the energy difference between the two levels. And so if we make a sort of semi-classical approximation, and then what we do is apply quantum mechanical corrections. And the corrections, these fudge factors, are known as oscillator strengths. So they give us a little bit of an idea about, for each transition, what is the correction that we need to apply. So we can now go back to lecture 1, where we were talking about the Einstein coefficients. And we can describe the line emission here as related to the Einstein A coefficient. And so we have a transition from the M state, or the M level, to the N level. And so that's denoted by these subscripts here. And we can think about the power that's emitted over some volume as being related to the photon energy that comes out, the number of atoms that are in the M level, right, that are available to give. So the M level is the higher level, and it's going to drop down to the N level, and it's going to give a photon. And then you have some probability here, which is really, is going to be related to these oscillator strengths. And this probability is the Einstein A coefficient. So if we think about this electron in the M state as being a harmonic oscillator, right, we can estimate the dipole moment of that electron as a function of time. It's going to change, and we can think about the charge times the position, and so it's going to just be going around, and it will be moving with some frequency, which we can think about as this frequency M to N. So it's dropping down from the M level to the N level, and so we can think about this as a harmonic oscillator sort of transition. And so then we can take the double time derivative of this, and we just calculate that out, and so we get something which is related to the frequency squared. And so the double derivative here is more or less given by this here, which is right, if we think about the average value, so taking into account that this oscillation the average value will be roughly 2, we get something which looks like this. And this here is just the average value of the position, which should be around 0. And so we can actually plug in this dipole approximation into our Larmor formula, right? So we have some acceleration of the electron as it goes from one level from the M level to the N level, and we have some sort of average value for this acceleration, and so the energy coming out will be related to that times some factors here, right? And so if we plug in what we have here, we end up with something which looks like this. So it has a frequency to the 4th power dependence, and then some constants. And so if we note that this power as a function of volume is kind of related to the power from an individual electron divided by the number of electrons, then we can estimate our coefficient here as being this oscillator power divided by the energy coming out. And so we can reduce one of the factors here of nu. And so this oscillator, or the Einstein coefficient, ends up being related to our frequency squared or frequency cubed times these factors, which are, this thing is going to be related to the atom, right? So the atomic number and so forth, whereas this thing is just constants. So we can, this thing here, we can, whoops, I'm going too fast. We can substitute this thing as thinking about from quantum mechanical perturbation theory, we can derive a similar formula as the dipole approximation. But instead of the dipole here, we have this thing, which is known as the electric dipole matrix element. And this thing is the, if you were to break down the transition from a quantum wave function of the m state to the n state, right, and take the average value of that and square it, this is what this dipole matrix is. So it's the sort of quantum mechanical version of our dipole approximation. But we have the same functional form here for this frequency dependence. And so if we calculate all these out, this ends up being that this Einstein coefficient is related to the dipole, the electric dipole matrix, is related to the frequency and some sort of value here, and this is in units of 1/2. And so this is a probability as a function of time that this transition will happen, right? So for the ground state of hydrogen, we can calculate these out pretty simply. And so this dipolar matrix is going to be approximately equal to our sort of classical electron radius times E squared. And so it generally is of the order of this. And we might make a slight quantum mechanical correction, at some point. And so for the ground state of hydrogen, we have this should be frequency, not V. I don't know if I can get a frequency out here. Let's see, I don't have anywhere to steal it from, so I have to make it. Oh, that isn't. Why is it in a weird? Must be the font. Yeah. Okay. All right. Very confusing. Okay. So frequency now. Right. So for the hydrogen atom and for the ground state, which has, if we go say from a 2-to-1 transition, so the Lyman alpha or whatever, it will have a frequency of this. We can think about the dipole as being the radius, right? And so then this is why we get this sort of, it's roughly proportional to this, the sort of radius squared. And we then plug that in, we plug this value in here into this, we end up with a Einstein coefficient that is about 10⁹ And so what this sort of means is, coming back to here, we have that this transition will have a probability of happening, which is related to this value. And so if we think about a classical oscillator, we can have a kinetic energy associated with that oscillator is proportional to, again, sort of in this dipole approximation, it's proportional to, the mv squared divided by 2. And so we can plug in our dipole here. And so we plug in our functional form in the averaged sense for this radius. And if we then look at the double derivative of the dipole, right, the acceleration term here, we get something which looks like this, and we can plug in these components back into here, and so this square of the dipole is going to look like our frequency squared, a couple of constants, and our kinetic energy. And so we can rewrite the Larmor formula to be the energy as a function of time. Looks like the minus this power coming out. It looks like this. And so now we have our charge here, and it's going to end up looking like this now. And so we can think about this as the total kinetic energy of the oscillator is related to this sort of functional form. And this is how much radiation is coming out, right? So this is how the change in energy as a function of time is related to the total kinetic energy, with this factor here being what's known as a damping constant. This is the sort of classical damping constant, not the relativistic factor. And so if we go back to our definition of the Einstein coefficient, in the classical sense, we had the Einstein coefficient is related to our oscillator power divided by our frequency. And so it's related to our oscillator power divided by T. And so it's related to this damping constant. And so if we do a similar sort of version of this, but for quantum mechanics, we get a slight variation, which is this fudge factor here. And so this fudge factor is known as the oscillator strength. And so this thing is the effective number of atom. It's in units of effective number of electrons per atom. And so plugging in our sort of values here back in, we have this thing times this, gives us our oscillator strength. And so you can go and calculate these oscillator strengths for different transitions in the atom. And then there's lookup tables where you could get out this value, or you could calculate it from first principles or from Monte Carlo simulations or whatever, to really do it. And this will then, as a function of the frequency of the transition, you will be able to get out an Einstein coefficient. And so then we can use the Einstein coefficient now for radiative transfer. And so recall we have the Einstein coefficient. So this was the spontaneous emission coefficient, which was the A1 to 2 coefficient. So with this one, and the fact that we have, we can relate the spontaneous emission to the absorption based on this ratio here, all right, or this sort of factor, and that the spontaneous and the absorption of the line and the stimulated emission of the line are related by these statistical weights. We can now plug in our functional form for the Einstein coefficient for this line transition. And now we have a similar one for the absorption. And so the absorption depends, again, on this oscillator strength, but has a different functional form for the frequency dependence. Because there's a frequency cubed here, there's a frequency squared here, and so we end up with a different frequency dependence for this one. And so with that, we can start to do radiative transfer, right? And we can understand, so if we have a photon field that is bathing an atom, there's some possibility that the atom will go from this state to this state, provided that there's a photon of the right energy right? And then that number of photons, there's some probability that if that photon is there, it'll be absorbed. And then you have a number of atoms in a volume, right? And so you can sum over the atoms in a volume, and you say, okay, what fraction of the light at this frequency, or very close to this frequency, is absorbed and pumps the atoms into the excited state. And likewise, then you can also factor in, okay, how long does it take, based on this coefficient, how long will it take for this to go back down to this and emit that photon back out? Right? And this is in terms of per second. And so, in effect, it's a probability as a function of time. Right? So if you have a certain number of atoms in the elevated state, then over time, you will see them drop down. And the probability of the rate at which they do that is dictated by this. That's all. Any questions? Most of this was just to, have you aware of the different nomenclature that's around, because you will see it in a lot of different places and in different forms. And so kind of to understand what it is and where to look for how to read it. What we're really going to be using in some details is this, right? Because this is how we relate emission and absorption processes of atoms, atomic level things, to macroscopic photon fields. Yeah? Any questions? No? Stop sharing.
I think that I have a question regarding the homework, but I don't know how to specifically ask. My question is more in the direction if I don't know if the methodology, or I don't know, the steps that I did to solve the first point are the specific right points, or I'm doing like something wrong or all wrong. I'm not completely sure about that, so I don't know. Because
so what's your question?
Yes, I mean, in the first point of the homework, do you asking about the energy density of the synchrotron radiation? So there is a equation that is regarding that the time escape of the electrons, that is like 3R/4C, and the term of a specific emissivity. I remember that is something like that.
Emissivity?
Yes. Oh, well, see, yes, emissivity. And
well, the radiation density, you simply get it from integrating the synchrotron component of the spectrum.
Yes, but in this case, in order to account for the self-absorption part of the spectrum, we didn't take into account that we have a different components. I mean, because, well, if we only consider the synchrotron part of the spectrum, with ignoring the self-absorption, well, the steps are more straightforward and it's more easy to find the energy density, but I don't know if this is properly.
Well, it's not necessarily self-absorption.
Ah, okay. Okay.
Right? And the self-absorption, that still, even if it was there, it comes into it, right? Because the photon field available to upscatter, that isn't going to be there because it's self-absorbed.
Okay.
Right, so it still counts.
Yeah, okay.
So you're overthinking the problem.
yes, it was the key. Okay, thank you.
Yeah, and I mean, you can also think about, would I really expect self-absorption up to the kink where that is? And I mean, you could just do a pretty straightforward calculation and estimate what conditions you will need to see self-absorption, like in the optical wavelengths. It's pretty extreme. Now, of course, the Crab nebula, the Crab pulsar is a pretty extreme object, but yeah, it turns out that the self-absorption portion is going to be below that.
Okay.
And,
Okay.
and largely what you're seeing is a break in the spectrum, which is related to the electrons.
Mhm.
Right? So you don't have just a power law that goes forever, but you have something which is actually a little bit weird. And so there's an injection term that's going there that then has some functionality to it, which, I mean, it's super cool and not necessarily super easy to understand, but that's what you're seeing there. But in terms of the inverse Compton, calculating what you need for inverse Compton, it doesn't really matter because you just want the photon field.
Okay. Okay, thank you.
Other questions? No? Okay. Bye, everyone.
Bye bye. Thank you.
Bye, thank you.